Water is a fraud, a cheat, a substance so common, so essential, that we forgive it for violating one of the most fundamental rules of physics in a spectacular and, fortunately for us, life-saving way. Almost every substance in the universe follows a simple and logical rule. When it cools and solidifies, its molecules come together, nestle closer to each other, and the material becomes denser. A piece of solid iron sinks in molten iron. Solid wax sinks in liquid wax. Solid gold sinks in molten gold. But water laughs in the face of this logic. When it freezes, instead of contracting, it expands. Ice, the solid form of water, is less dense than its liquid form, and because of this, it floats. You see this every time you put an ice cube in a glass of water. It seems banal, normal, but it's not. It is such a profound anomaly, such a rare and bizarre exception, that it is fair to say that if water behaved normally, none of us would be here to discuss the matter. Life on Earth in its entirety owes its existence to this miraculous peculiarity. Imagine what would happen in a world where water obeyed the rules. In winter, when the temperature dropped, the surface of a lake would begin to freeze. But ice, being denser, would sink. Then, the new layer of water exposed on the surface would freeze and sink as well. And so on, layer by layer, until the entire lake, from bottom to surface, became a solid block of ice. Any fish, any plant, any form of aquatic life would be crushed and frozen. The cycle of life would be interrupted each winter. In the oceans, the ice that forms at the poles would sink to the bottom of the sea, where the pressure is immense and sunlight never reaches. The world's oceans would gradually fill with ice from the bottom, turning our planet into a snowball from which it might never recover. But that's not what happens. What happens is that the ice floats. It forms an insulating layer on the surface of the water, protecting the liquid life below from the freezing temperatures of the air. This layer of ice acts like a blanket, ensuring that even in the harshest winters, the lakes and oceans remain liquid underneath, allowing life to continue. I love this problem. I love it because it's the perfect example of how an everyday observation, something a child might point out, can take us on a journey into the depths of molecular chemistry, thermodynamics, and the very history of life. There's nothing more exciting than taking an obvious fact and asking why exactly. Let's do this together. Let's become molecular detectives. The crime scene is a glass of water. The victim is the law of density. The culprit, a tiny molecule with a funny shape that refuses to follow the rules. Let's unravel the structure of the water molecule, understand the strange forces that act between them, and see how these forces conspire to create the crystalline structure of ice that is emptier than the mess of liquid. We won't need a laboratory, just our imagination. And in the process, we'll discover that the same principle that makes ice float is also responsible for a series of other strange properties of water that make it the most extraordinary and vital substance on our planet. To understand the anomaly, we first need to understand the rule. Why do things typically become denser when they solidify? Imagine a dance hall full of people moving freely. They are warm, full of energy, and maintain a certain distance from each other. This is the liquid state. Now, start cooling the hall. The people lose energy, move more slowly, and begin to get closer, snuggling together to conserve heat. Eventually, they stop moving completely, becoming shoulder to shoulder, as compact as possible. This is the solid state. The same people, molecules, now occupy less space. The mass is the same, but the volume has decreased. Therefore, the density, mass divided by volume, has increased. This is the natural tendency. Atoms and molecules, upon losing thermal energy, want to find the lowest energy state, which is usually the closest and most compact possible, where the attractive forces between them are maximized. It's a simple and elegant rule, driven by the pursuit of stability. And it's the rule that water breaks so spectacularly. The secret to the crime lies in the identity of the culprit, the water molecule, H2O. It is composed of one oxygen atom bonded to two hydrogen atoms. But they are not in a straight line. The bonds form an angle, giving the molecule a V shape, or, as I like to think of it, Mickey Mouse's head, with the oxygen being the head and the hydrogens being the ears. Now, the oxygen atom is a little greedy for electrons. It pulls electrons from the hydrogen atoms closer to itself. The result is that the oxygen side of the molecule has a slightly negative electrical charge, and the hydrogen sides have a slightly positive charge. This makes water a polar molecule. It has a positive pole and a negative pole, like a small magnet. This polarity is the key to everything. It's what allows water to dissolve so many substances, hence the name universal solvent. And it's what makes it behave so strangely when it freezes. This simple asymmetry in charge distribution transforms a seemingly trivial molecule into one of nature's most complex and fascinating compounds. This polarity gives rise to a special force between water molecules. The positive side, hydrogen, of one molecule is attracted to the negative side, oxygen, of a neighboring molecule. This attraction is called a hydrogen bond. It's important to understand that it's not as strong a bond as the bond that unites the atoms within the molecule itself. It's a weaker, intermittent force, like a handshake between molecules. The discovery and understanding of this bond was a major step in chemistry, largely due to the work of chemist Linus Pauling. He realized that this force, although weaker than covalent bonds, was strong enough to drastically influence the properties of a substance. In liquid water, these hydrogen bonds are chaotic. They constantly form and break every picosecond. The molecules are in a state of frenetic dance, constantly switching partners. This keeps them relatively close to each other in a compact and disordered mess. It is a dense, cohesive liquid held together by this transient network of handshakes. Now, let's freeze the water. As the temperature drops, the molecules lose energy and move more slowly. The frenetic dance calms down. The hydrogen bonds, which were once fleeting, now have time to form more stably, and they don't want to form haphazardly. Remember, each water molecule has two hydrogens, positive, and one oxygen, negative, with two lone pairs of electrons. It wants to make exactly 4 hydrogen bonds with its neighbors, in a very specific geometric orientation called a tetrahedron. To satisfy this need to form 4 perfectly spaced bonds, the water molecules begin to organize themselves into a highly ordered and repetitive structure. They can no longer pile up randomly. They are forced to maintain a certain distance and at a certain angle from each other, so that all the hydrogen bonds fit together perfectly. They exchange the disordered proximity of the liquid state for the ordered, but distant beauty of the solid state. And it is this forced distance that changes everything. The structure that water molecules form when freezing is a hexagonal crystalline lattice. Imagine a 3-dimensional honeycomb. It's an incredibly beautiful structure, full of symmetry, and it's the reason why snowflakes have 6 sides. But most importantly, this structure is remarkably open. It's full of empty space. The molecules, by locking together in this hexagonal formation to satisfy hydrogen bonds, end up occupying more space than when they were sliding over each other in the liquid state. The average distance between molecules in ice is greater than in the liquid. It's as if the people in our dance hall, instead of crowding together, decided to hold hands and form a large circle. For everyone to connect correctly, they need to move away from each other, and the circle ends up occupying much more space than the crowd of people. The result is that the same number of molecules now occupies a larger volume. The mass is the same, the volume has increased, and therefore the density has decreased. And that's why ice floats. It's not magic. It's molecular geometry. Let's visualize this molecular dance in more detail. In liquid water, at room temperature, the molecules are in constant motion, like people in a crowded market. Hydrogen bonds form, stretch, break, and reform in the blink of an eye. The molecules are, on average, very close to each other. As the temperature drops, the movement slows down. The molecules begin to form more stable clusters, small islands of ice-like structure that form and break apart. The water begins to become denser, like most liquids. But then something strange happens around 4 degrees Celsius. Below this temperature, the formation of the open hexagonal structure begins to dominate over the effect of thermal contraction. More and more molecules fit into this spacious network. The net result is that the water begins to expand, becoming less dense. At 0 degrees Celsius, during the transition to ice, this expansion becomes dramatic. All the remaining molecules lock into the crystalline structure, and the volume increases by about 9%. This transition from compact disorder to spacious order is at the heart of the water anomaly. The consequence of this physics doesn't have a single famous equation, but it can be seen in a graph that physicists love: the phase diagram of water. This graph shows the state, solid, liquid, or gas, of water at different temperatures and pressures. For most substances, the line separating the solid and liquid phases slopes to the right. This means that if you take a solid and increase the pressure, it will remain solid. In fact, you force it to become even more solid. But for water, this line slopes to the left. This means that if you take ice and apply pressure, you can make it melt and turn into liquid. Why? Because the liquid state is denser. Pressure favors the more compact state. This is why ice skaters can glide so smoothly. The thin blade of the skate exerts enormous pressure on the ice, melting a very thin layer of liquid water that acts as a lubricant. As soon as the skater passes, the pressure is relieved and the water freezes again. Ice flotation and ice skating are two sides of the same anomalous coin. A thought experiment, or a very real household accident for those who live in cold climates, demonstrates the incredible power of this expansion. Leave a glass bottle full of water outside on a freezing night. The next morning you will find the bottle shattered. What happened? The water, upon freezing, expanded. And this expansion is not a weak force. The pressure exerted by the water as it turns to ice can reach hundreds of atmospheres, enough force to break glass, burst metal pipes, and even crack rocks. This phenomenon, called ice wedge action, is one of the most powerful forces of geological erosion. Water enters small cracks in the rocks, freezes, expands, and widens the crack. Cycle after cycle, over thousands of years, entire mountains can be sculpted and demolished by this silent and relentless force. Therefore, the same principle that makes an ice cube float gently in your drink is powerful enough to reshape the surface of our planet. It is a striking demonstration of how effects at the molecular scale can manifest as monumental geological forces. The behavior of water becomes even stranger and more crucial to life when we look closely at what happens before it freezes. As we have seen, water does not become progressively denser until it reaches its freezing point. It reaches its maximum density at approximately 4 degrees Celsius. Below that, it begins to expand and become less dense. This has a vital consequence for aquatic ecosystems, a phenomenon called lake stratification and turnover. In the fall, as the surface water of a lake cools, it becomes denser and sinks, pushing the warmer, less dense water from the bottom upwards. This mixes the lake, distributing oxygen and nutrients. But when the surface water reaches 4 degrees, the process stops. If it cools further to 3 degree, 2 degree, 1 degree, it becomes less dense and remains on the surface. It is this top layer that eventually freezes at 0 degree, forming the floating ice sheet. The denser water, at 4 degrees, remains safe at the bottom, providing a stable refuge for fish and other life forms to overwinter. Without this 4 degree anomaly, the lakes would freeze from the bottom up. Now, an honest scientist should ask, is water the only substance that does this? The answer is no, but it is the most famous and by far the most important. A few other substances also expand upon solidification, such as silicon, gallium, bismuth, and antimony. It is interesting to note that silicon, the basic element of all our electronics, shares this anomaly with water, the basic substance of all our biology. But for the vast majority of the millions of known chemical compounds, the rule is clear. The solid is denser than the liquid. What makes water so special is its omnipresence and its central role in life. No other substance with this property exists in such abundance on the surface of a planet and serves as a solvent for the biochemical processes of life. The rarity of this property across the entire chemical spectrum highlights how lucky we are. Life not only found a way to exist with water, it could only exist because of water's bizarre and exceptional properties. The importance of hydrogen bonds and the structure of water extends to all areas of science. In biology, it's not just floating ice. The way long DNA molecules maintain their double helix structure crucially depends on hydrogen bonds. The way proteins fold into their complex functional shapes is largely dictated by their interactions with surrounding water molecules. The very structure of the cell membrane is a dance between hydrophilic, water-loving, and hydrophobic, water-hating parts. In geology, as we've seen, ice wedges sculpt mountains and create soils. In climate science, ice fluctuation is fundamental. The vast polar ice caps have a high albedo, meaning they reflect a large portion of sunlight back into space, helping to regulate the planet's temperature. The loss of this ice not only raises sea levels but also lowers Earth's albedo, causing it to absorb more heat in a dangerous feedback loop. The water anomaly is not a mere curiosity. It is a central player in the planetary system. When we turn our gaze to the stars, the anomaly of water takes on cosmic importance. In the search for extraterrestrial life, the mantra of astrobiologists is "follow the water." The habitable zone around a star is defined as the region where temperatures allow for the existence of liquid water on a planet's surface. But perhaps that's not enough. Perhaps we need to look for planets where liquid water can persist. On a planet with seasons like Earth, if water behaved normally, its oceans could freeze solid, perhaps irreversibly. The property of floating ice may be a second requirement, an additional filter for habitability. Any planet that harbors complex aquatic life will likely need its life solvent to have this same anomalous property. Therefore, the search for life may not just be the search for water, but the search for the consequences of hydrogen bond geometry. A search for a peculiarity of chemistry that may be a universal prerequisite for biological existence as we know it. This leads us to an almost philosophical question. Was it pure luck? Did the universe simply produce a set of physical laws and constants that, by chance, resulted in a water molecule with a bond angle of 104.5 degrees, which in turn leads to hydrogen bonds that form a less dense ice structure, which in turn allows life to evolve and sustain itself? It's a chain of remarkable coincidences. Some might see this as evidence of intelligent design, or a fine-tuning of the universe for life. As a physicist, I tend to be more cautious. Perhaps there are many universes, each with different laws, and we simply live in the one where the laws allowed our existence, the anthropic principle. Or perhaps we don't yet understand fundamental physics deeply enough to see why these properties are unavoidable. But regardless of the final answer, we can't help but feel awe. We exist because of a chemical accident, a flaw in the rule. And that, to me, makes reality all the more beautiful and precious. Can we use this strange property to our technological advantage? Yes, and we already do, although there is much more potential. One interesting field is freeze-drying desalination. When seawater freezes, the crystalline structure of the ice tends to expel impurities, such as salt. The ice that forms is largely pure water. By carefully controlling the freezing process and then separating the ice from the remaining brine, we can produce fresh water. While still less common than other methods, such as reverse osmosis, it is an active area of research. On a more fundamental scale, scientists are exploring the use of ice structure as a model for creating nanomaterials. By freezing solutions with other molecules, it is possible to use the crystalline lattice of ice to organize these molecules into new structures, which may have interesting electronic or optical properties. Understanding and harnessing water crystallization, the phenomenon that nature uses to protect life, could give us new tools to build the future. And, as always in science, the more we learn, the more we realize we don't know. Water remains one of the most mysterious substances in existence. Although we understand the basics of the structure of floating ice, called each ice, there are at least 17 other known crystalline forms of ice, formed under different pressure and temperature conditions, each with its own structure and density, and most of them, incidentally, are denser than liquid water. Scientists are still intensely debating what happens to supercooled water, liquid water below 0 degrees that has not yet frozen. Some theorists propose that it may exist in two different liquid forms, one of high and one of low density, an idea that is still at the frontier of experimental research. The most common substance on our planet is still, in many respects, a terra incognita, a humble reminder that even the most familiar things can hold the deepest secrets. So, let's recap the solution to our mystery. Why does ice float? First, we learned that the water molecule is polar, V-shaped, which makes it a tiny magnet. Second, this polarity leads to the formation of hydrogen bonds between the molecules, which are like directional handshakes. And third, when water freezes, these hydrogen bonds force the molecules to organize themselves into a hexagonal crystalline structure, which is very beautiful, but also very spacious and full of holes. This ordered structure occupies more volume than the disordered mess of the liquid state, resulting in a lower density. The floating of ice is not a magic trick. It's an inevitable consequence of molecular geometry, a direct result of how H2O molecules decide to shake hands when the cold sets in. The lesson to take home is this: the next time you put ice in your drink, stop for a second. Don't just see a frozen cube. See the tetrahedral dance of water molecules. See the hydrogen bonds locking into a hexagonal lattice. See the anomaly that breaks the rules of physics. And see the reason why lakes don't freeze from the bottom up, why fish survive the winter, and why life ultimately had the chance to flourish and persist on our planet. You're not just cooling your drink. You're holding in your hands a piece of the cosmic accident that allowed us to be here. Appreciating science isn't just about understanding the exotic and the distant. It's about discovering the miracle hidden in the heart of the ordinary. It's seeing the grandeur of the universe in a simple glass of water. I conclude with this thought: nature is more ingenious than any engineer. It uses flaws and exceptions to create opportunities and complexity. What appears to be a violation of a rule is often the gateway to a new level of organization. The anomaly of water teaches us that we should not fear irregularities and exceptions. We should celebrate them. We should seek them out. They are the clues that nature leaves us, pointing to a deeper and richer understanding of reality. There is nothing more exciting than finding one of these clues and following its trail. Therefore, keep your eyes open to the small oddities of the world around you. Ask why things are as they are, especially when they seem to make no sense. The greatest intellectual adventure begins with the courage not to take the world for granted, but to marvel at it in all its gloriously imperfect details. Now that we've uncovered the secret that allows life to swim beneath a blanket of ice, what other pillar of our existence should we investigate? We've already talked about time, screens, light, and matter. What else in our daily lives hides a secret of physics that defines our world? Perhaps we should talk about friction, the force that simultaneously wears us down and allows us to walk. Or about sound, the vibration of air that transforms into music and language inside our heads. Leave your suggestion in the comments. What's the next piece of the universe's puzzle you'd like to assemble with me? And remember, nature is full of surprises, and the most beautiful of all might be floating in your glass right now.